Okay, hi guys, welcome back. We're in Math 352. We're up to lecture 12 now, and I'm going to do this lecture in two parts because they're going to be quite distinct. The first part, what we're going to do is we're going to take what we did with the simplex method in lecture 11, and we're going to apply it to a small concrete example so we can get a much better feel for what's going on with this. Okay, so that's where we're going to begin. So I'm going to set up a standard form linear program, and we're going to use the simplex method to solve it. Okay, so example. Let's have a look at what it is. So we've got the LP where we've got to minimize, as usual, C transpose X, subject to, in standard form, some equality constraints and some non-negativity constraints on our X variables. Okay, so for our example, we're going to have a 2 by 4A, which is negative 1, 3, 2, 1, 1, 0, oops, 1, 0, 0, 1. We'll have B equals 4, 9, and C transpose is equal to negative 1, negative 2, 0, 0. Okay, looking at our matrices here, you can see that matrix A looks very much like an inequality form LP has had a couple of slack variables applied to it. It's got that giveaway identity matrix tucked in at the end there. Okay, now to start the simplex method on an LP, we need an initial basic feasible solution. I haven't really talked about how to do that yet, but for this one it's actually quite obvious. Okay, the last two columns are linearly independent already. So I'm going to choose as my initial basis B to be those last two columns because they're nice and simple, and N will therefore be whatever's left over. That will be 1 and 2 in this case. Now looking at those equations there, in general there's no obvious way of just doing this for a general LP. Okay, as I'll show, I'm just going to be lucky here that I've made a good choice. Okay, so AB is therefore equal to columns 3 and 4 of A. So it's going to be 1, 0, 0, 1. And our initial XB, which, because we've chosen 3 or 4 as the variables x3 and x4, equals AB inverse B. Well, AB is just the identity, so is its inverse, and AB inverse B will just be B, equals 4 and 9. Okay, XB is greater than or equal to 0, therefore our initial basic solution is feasible because of the non-negativity of each of the variables. So B gives an initial basic feasible solution. Now once again, I'm going to stress we can't just get an initial basic feasible solution usually. Kind of lucky in this case that we can do that, but we'll talk about some systematic ways of finding that a little bit later. So we can start the simplex method. Okay, so we've got ourselves an initial basis, and that's all that works. That gives us a feasible x, so we can get going. Okay, so I'm just going to go through this iteration by iteration until I can stop. So iteration 1. Well, we start by computing the reduced costs. Okay, and if you look at your notes from lecture 11, this was equation 6 or 11.6, and that's R equals Cn minus An transpose AB inverse transpose CB. Okay, so plugging in the various pieces, Cn, well, that n is, don't remember, B equals 3, 4, n equals 1, 2. Cn is just the first two entries of C, so it's going to be -1, -2, minus An. An is the first two columns of A, transpose. AB was the identity, inverse transpose, times CB. CB is the third and fourth entries of C, which is just 0, 0. Okay, and you can see obviously this last term is just going to multiply out to 0, so our reduced costs are just -1 and -2. Okay, so just to refresh what that means, you don't need to do this in general when you're doing a simplex method, but just to remember that C transpose X is equal to, if we're solving for that in terms of the non-basic variables that we're thinking about entering in, we get CB transpose current xk plus R transpose xn. Okay, so that's our cost in terms of the non-basic variables as we start moving them around. And because they're negative, we have negative entries in there, increasing the corresponding non-basic variable is going to decrease our cost. Okay, if one of these xn's becomes positive, it's currently 0, then the cost will go down. Now CB is 0, so in our case that means we get 0 minus x1 minus 2x2. Okay, so for this vector r, we can see that we could either choose x1 or x2 to be our entering variable, as they'll both give us a reduction in the cost. And as a standard type of thing, you choose the one with the most negative entry because, well, it sort of seems like you'll get there faster. Okay, like I said last lecture, it's not a hard and fast rule. There are other ways of choosing variables in the simplex method. But that's probably the most standard one, I think. Okay, so R has two negative entries. And -2 is the most negative. So we choose the entering variable xe to be x2. Okay, so we want to make x2 enter our basis, and we're going to remove either x3 at x4 or x4. Okay. Now remember what we're doing is we're going to increase x2 until one of x3 or x4 drops to 0. So looking back to our notes on simplex, we compute the vectors b hat equals a b inverse b, which is 4, 9. We've already done that in fact. And and d equals negative a b inverse ae. So for our example, the entering variable is 2, so our entering column is going to be a2. And that gives us, well, AB inverse is the identity, negative that is negative the identity, so it's going to be negative A2. So it will be -2, -1. Okay, so this is equation 11.8 in your simplex lecture, in the simplex lecture notes. Okay. Both entries are negative of D. Because remember, we're only going to consider the ratios where D is negative. So we compute both ratios. B hat 1 over negative D1. Well, that just gives us -2. and b hat 2 over negative d2. That gives us 9 over 1, which equals 9. Okay, so remember these two numbers are possible values we could choose that would make the basic variables go to 0. So if we chose x2 equals 2, by that stage that would have made our first basic variable, which is x3, go to 0. And if we continued increasing x2 all the way up to 9, that would make our second basis variable, x4, go to 0. Now we always choose the smallest of these, because if we go any further, we're going to violate the non-negativity constraints. The first ratio is smaller, so we choose the first entry in the basis to be the x3, to be the leaving variable. Okay, and replace it with x2. Okay, because we decided that x2 was going to be our entering variable. So our new basis, we just replace the entry we took out. So we've taken out x3 and we've replaced it with x2. So our new basis is going to be 2, 4. Notice we keep the order of the variables in the basis intact. And the new non-basic variables are going to be 1 and 3. So what we've done is we've done one whole iteration of the simplex method. Okay, and yes, let's go into the next one. So what we do now is we just start again. Iteration 2. We've got us a basis. Our basis is 2, 4. Our non-basic variables are 1 and 3. So once again we start with the reduced costs. R is once again Cn minus An transpose A B inverse transpose CB equals negative 1, 0 minus An, so that's going to be columns 1 and 3 of A now. Negative 1, 3 and 1, 0. AB inverse transpose, well AB is columns 2 and 4. And we have to take the inverse and the transpose of that. CB, that's the second and fourth entries of C, negative 2 and 0. And if you multiply that out in MATLAB or by hand, it's small enough to do by hand pretty easily, you get negative 2, 1. Now this time we've only got one negative entry in our reduced costs. So only the first non-basic x1 has a negative entry. Or negative reduced cost. So we choose x1 to be the entering variable. Okay, so once again we compute those two vectors that we're going to take ratios of. B hat equals A, B inverse B. In this case you can work it out for yourself. You get 2, 7. And D equals negative AB inverse AE. Okay, that's the entering column. Now our entering variable is x1, so it's going to be negative AB inverse A1, the first column of A, which if you work that out gives you 1/2 of 1, negative 7. Okay, so now we go to computing those ratios to see which values we need that will make see what we can increase x1 to make one of the basic variables 0. Now remember, we only consider the entries where we've got negative d, so only the second entry of d is negative. So we don't even need to compute the ratio at all. So the second entry in the basis x4 automatically becomes the leaving variable. Okay. So the new basis therefore is b. So x4 is going to leave our basis, x1 is going to enter it, x2 stays where it is, and in our non-basic variables, x1 left that and got replaced by x4. Okay, and we're on to our next iteration. So you can probably guess that we're going to finish on this one, and let's verify to see whether that's true or not. So iteration 3. We haven't actually got that many more options in terms of vertices we can consider. So now we've got b equals 2, 1, and we've got n equals 4, 3. So first we compute the reduced costs, just as we have been doing. R equals Cn. Just using that formula over and over again. By the way, this is the type of formula that I definitely give you in a test or an exam. Kind of hard to remember, but use it all the time if you're doing this by hand. So plugging the various pieces in, Cn is now 0, 0, because it's the third and fourth entries of C, minus An transpose, which is 0, 1, 1, 0. Okay, it's the fourth and third columns. Notice the order is important there. AB is 2, 1, negative 1, 3. Inverse transpose CB. Once again, if you do a bit of work and solve that by hand, you get 1/7 of 4, 5. Okay. R is greater than or equal to 0, so we have found so we have found the optimum. Okay, so let's just sort it out. So xb, therefore, our optimal basis is x2 and x1, and solving for those is AB inverse B equals 3, 2. Xn, the non-basic variables, don't forget, at any basic solution, the non-basic variables are always 0. Only the variables inside the basis can be non-zero. So, to put it all together, our optimal x star, just piece the variables together in the right order. x1 is 2, x2 is 3, x3 and x4 are both 0, and our optimal cost is worth figuring that out as well. C transpose x star is equal to, well, remember that C was negative 1, negative 2, so it'll be negative 8. And we are done. Okay, so we've basically done the simplex method on a problem, and it's taken us 3 iterations, and we eventually, inevitably, got to an optimum of our problem. Okay, now this one here, as I kind of alluded to at the start, this problem has come from a nice inequality form problem. So if we go back to our problem, actually I'll just write it down here, we can express problem as, so let's just find the question, as minimize, let's see, it's negative x1 minus 2x2, subject to, what have I got? I've got two equality constraints, negative x1 plus 2x2, and I'll rename x3 and x4 s1 and s2 just to make it even clearer what's going on. Equals 4, 3x1 plus x2 plus s2 equals 9. Okay, so what we really had was an inequality form LP, where we had these inequalities, which we've converted to equalities by our standard form procedure. So these are really these two inequalities here. Okay, and we've also got x1 is greater than or equal to 0, and x2 is greater than or equal to 0. Okay, so that's our problem. Why don't we just have a sketch of what happened in our LP as we solved it? Okay, so x3 and x4 were the slack variables. Okay, so let's just draw up a picture of this LP. So what have we got? We've got x1 is greater than or equal to 0. Yeah, that's this one down here. But why don't I even change color? Okay, x2 is greater than or equal to 0. Negative 1 plus 2x2 is less than or equal to 4. If I rearrange that, I get x2 less than or equal to x1 over 2 plus 4. Okay, so that's a line starting at 4. With slope like this. Slope a half, so it kind of goes up like that. And this one here gives us x2 is less than or equal to negative 3x1 plus 9. Okay, so a line starts up at 9, it's probably about there, and has a slope of negative 3. Okay, whoops, sorry, that's just a small mistake there. That should be x1 over 2 plus 2, shouldn't it? Okay. Right, so let's just fix our picture. It should be a 2, not a 4. And our slope is still a half. Okay, so that'll be 3. That will be... and these two lines will intersect. Well, that's going to have gone down from 9 to 3. So that point there is going to be 2. That point there is going to be 3. Okay, and we can shade out the outside of these. Okay, so our feasible region for the problem is that area just here. Now let's just have a look at what happened from iteration to iteration. Okay, so in the first iteration, I'll just look at the non-basic variables. Our non-basic variables n were the variables 1 and 2. Okay, this means that x1 equals 0 and x2 equals 0, and our slack variables x3 and x4, they equaled something. So we started here at iteration 1. Okay, at our second iteration, what did we do? Well, we plugged in 2 into our basis and our non-basic variables. So we had, n equals 1, 3. That means x1 equals 0, and S1 equals 0. Okay, so S1 is the slack variable corresponding to this constraint here. And if the slack variable is 0, then it means we're on this constraint, on the line. Okay, so we moved along here to this point here. And that was where we got to at iteration 2. Okay, we then, at iteration 3, we had n was equal to, what was it, 4 and 3. That means we had S1 equals 0 and S2 equals 0. And what that means, the slack variables corresponding to each of these two constraints here, the two slopey ones, they're both 0. That means we're on the boundary of each of those constraints. So we must have moved to this vertex here. Okay, and then when we got to there, we found that we couldn't go anywhere. We couldn't go any further to make our cost smaller. Okay, so that makes sense. And if you look at the gradient vector, grad f equals negative c equals 1, 2, that looks something like this. So we've basically, you can see if we were solving this by the graphical method, we've gone as far as we can in that direction in our feasible region. Okay, so you see that what happens is basically at each step of the simplex method, we are at the intersection of two constraints for a two variable problem like this, and each step we switch to a different set of two constraints. We replace one of the constraints with another one, and that moves us along an edge towards closer and closer towards our final solution. Okay, so I'm going to stop there. There's an example. We're going to come back to the second half of this lecture shortly, and we're going to start looking at the phase 1, what we call the phase 1 problem. Okay, the phase 1 problem is the problem of how do we find an initial basic feasible solution to start with. Okay, I was kind of fortunate for this problem that I just sort of pulled one out of the air, but in general it's not straightforward to do this, so that's what we're going to address next.